welcome back to Coffee Shop Astrophysics. So, just before we get started, we'd like to tell you about some of the cool things that you can see coming up at the UWM Planetarium. So, you can see some of them are done, but there's quite a bit left. So, yeah, be sure to check that out. And just a reminder, if this is your first time at Coffee Shop Astrophysics, we are graduate students from UWM. We're with the Center for Gravitation Cosmology and Astrophysics, and we come here every once a month during the school semester to give a talk about some fun astro or other physics stuff. So be sure to join us at our next couple of talks, and we will let you know about when those are. So if you have any ideas for a coffee shop talk that you'd like to see or some science stuff that's really cool and you'd like to see discussed, do let us know at our email address. But today, our topic is, oh, before we get started, yeah, we have our speakers. I'm Shashwat and this is Gabe, and we are going to be talking about the sounds of space. So if you hear that, it sounds really creepy, and we will get into what that is exactly. But that is an example of a sound of space. So let's start with the basics. What is sound? Sound is just the compression and expansion of a material or what we call a medium. And usually that's air, just because we talk around and you hear my voice through the air. So these pressure changes are picked up as waves, and your eardrums can tell can perceive them as sound. All right, so what are the properties of sound waves? You've heard of light waves, and they are similar, but sound always needs a medium or a material to go through. Light can just go through empty space. So, like light waves, sound waves have a wavelength, they have a frequency, and they have an amplitude of how loud they can be. So, it's usually represented by like a simple sine or cosine wave because they have a frequency, a wavelength, and an amplitude. But let's talk about the speed of sound because it's a lot weirder than the speed of light. We all know the speed of light is the fastest in the universe. It's around 300 million meters per second. But the speed of sound is much slower, and like I said, it needs to travel through something. So when we're talking about air, the speed of sound is roughly 340 meters per second, or shy of 800 miles per hour. So that's pretty fast, but it depends on the temperature. So on a colder day, it'll probably be a lot slower. If there's more humidity, it might be a little faster. And so in water, the speed of sound travels a lot faster at 3,300 miles per hour. In aluminum, it's up to 14,000 miles per hour, and diamond at 27,000 miles per hour. So that's a really long diamond. The denser and the hotter a medium is, the faster the sound can travel through it. So here we've got an image of what the speed of sound looks like as you go up the atmosphere. So as you get higher, you can see there's a temperature curve right here, and it kind of wiggles all about. But the speed of sound closely follows that. So it really depends on the temperature of a material. So what exactly can we hear? We'll talk about the amplitudes, but first let's talk about the frequency. So when we talk about sound or music, we usually mention pitch. And it's important to make a distinction. Pitch is subjective, so everybody hears pitch differently, whereas frequency is like an absolute. It is a physical property of the sound. So that's one key difference about the two. So humans can hear from 20 to 20,000 hertz, and that's a pretty big range. But as you get older, that range actually goes down. So older people probably won't hear higher frequency noises around 18 to 20,000 kilohertz. I personally have checked; I can hear up to 17,000. So my range is shortened. Bats and dolphins tend to use like sonar or ultrasonic, so they can hear much higher frequencies. So can dogs. And here's just a diagram of what the human ear looks like. It looks really weird, but sound is picked up by an eardrum, and a bunch of bones uh, help the vibrations travel into your inner ear, where there's a fluid that picks up the vibrations. So it's pretty wild inside your ear. But here's just the range of frequencies, and let's see how many of them you can hear. And I'm going to stop it around the 1 kilohertz range because it does get very, very annoying. But yeah, so as if you could have heard, maybe at the very, very low frequencies, you didn't pick anything up until, yeah, some of you may remember that noise. But yeah, so we're going to be talking about the decibel scale. So last time we talked about frequency. This time it's more about amplitude. So we measure sound in intensity, which is power per area. So how much power is being put into a certain area. And about the lowest we can pick up with our ears is 10 to the minus 12 of these, which is really, really small. So your ears are extremely sensitive. And we use the decibel scale because we deal with very large ranges of numbers. So this is actually logarithmic, kind of like the Richter scale for earthquakes, which we'll actually be discussing later on. But basically, we set 0 decibels to be the lowest thing we can hear, and increasing it by 10 decibels is multiplying it by 10, increasing by 20 is multiplying by 100, increasing by 30 is multiplying by 1,000. So you take the log of the ratio of intensities and multiply by 10. So basically, when you add, you're actually multiplying in intensity scale. So that might be a little confusing, but it just multiplies instead of adding. Yeah, so let's talk about something much cooler now. Let's talk about shock waves. A shock wave is basically what happens when a material is traveling through the medium much faster than sound can make it. So, like I mentioned, the speed of sound is 760 miles per hour, and we call this Mach 1. So when jet planes travel faster than Mach 1, they break the sound barrier. In this gunshot here, you can probably see when the bullet is traveling here, it's all these pressure waves are coming off of it in these circles, but since the bullet's traveling too fast, it forms more of a cone because the pressure waves can't catch up with it. So that's called breaking the sound barrier. And what's interesting is here, when jet planes break the sound barrier, you see what's called a vapor cone, and that's because the moisture in the air gets compressed and turns back into water. So you're seeing water vapor being turned into water. And you can also see it at the top of this volcanic explosion here. Some of the shock waves end up forming clouds. So shock waves are pretty cool. But this presentation is called The Sounds of Space. And as far as I know, there is no sound in space. There's nothing for it to travel through, right? There's no air. Well, there's a bunch of stuff in space. And while there's not enough for us to be able to hear sounds, there is a lot of effects that sound does have in space. So there's a lot of material, just like dust, ice, gases. In nebulae, which are the remnants of dead stars, you have a lot of material just spread out over an area. And these pressure waves within the material can send out shock waves as well. And on planets like Saturn, you have a lot of these sound waves forming giant cyclones, hexagonal shaped cyclones at one of the poles. On much larger scales, you can have some of this dust and gas eventually collect in a small space because of these sound waves leading to the formation of stars. So pressure and sound does have an effect within space. So let's talk about the solar wind. I mentioned that some of the air in space is kind of solar wind. Well, the sun is very energetic. It has a lot of plasma, and this is charged material. So these are gases that have been ripped of their electrons, and they move over magnetic field lines like this. And as the star turns, these magnetic field lines twist, and eventually some of this material is actually thrown off of the sun and comes flying towards us. So you have things that are like coronal mass ejections, where a large amount of material is spit out from the sun. And the sun's magnetic field is actually really big. So you can see that its influence goes beyond the solar system. And at this point called the termination shock, it begins to travel slower than the sound that can travel within this area. So you've got a shock wave that forms here. Yeah, the sun is also affected by wind from outside, from other stars. There's a lot of stuff going on. But let's go loud, because everyone likes explosions and loud things. So let's talk about supernovae. One of the most important types of supernovae for astronomers is what's called a type 1a supernova. And it helps us measure distances extremely well because we have an idea of how much energy this releases. So this occurs when you have what is called a white dwarf that accretes material and basically explodes. So what is a white dwarf? Well, a white dwarf is a dead star. It's the core of a star about the size of the sun or slightly higher. And there is no fusion taking place within it, so it's just a hot, dense ball that's slowly cooling off over time. Our sun will probably end up here, and they're usually made up of carbon, oxygen, or slightly higher elements. And if they have a partner around them, they can actually start to take material off of the star, start stealing and stripping the star off its own atmosphere, and this eventually ends up creating fusion again, which leads to an explosion. So we know that type 1a supernovae are around 10 to the 44 joules. That's not really a number that makes sense. To put it colloquially, that's 44 followed by 36 zeros worth of Big Macs of energy if you were to eat that. But yeah, this is released in just a few seconds in an object the size of the Earth. So that's a lot of power in a small amount of area. And that's about 10 to the 29 watts per meter square. I wouldn't worry if that's a hard number to get your head around, but like I did mention, the smallest intensity is 10 to the minus 12. So this would be 410 decibels loud. And a jet plane is about 140 to 160. So this is extremely loud if you were at the surface. I would not recommend. All right, so how do we hear sounds from distant objects? There must be a way. You must have seen some of the videos that show you sounds of things. And there's a neat trick we do. We look at the light coming from these things, and we basically measure the light waves, and since they're both waves, we convert one to the other. And sometimes the light waves may be too low to hear, so they might be in this frequency range, and we have to pitch correct so that we're able to hear it. But you do have light that lies within the human hearing range. These are called radio waves. So you have radio waves of about 1,000 hertz or 10,000 hertz, which you can hear. And the solar wind actually creates these radio waves when it interacts with planetary surfaces. So Gabe will show you some cases where the magnetic fields of planets actually sing to us because the solar wind interacts with it. Let's see if I can get this sound to play. Is it? Okay, I guess not. But that was just 1,000 hertz to show you that radio waves do lie between human hearing range. So we can take a look at stars and how their light changes because of all the weird things going on inside them. They have a lot of different processes that create sound waves that bounce in and around stars, and this changes the light over time. So we can take a look at how this light changes and form like a sinusoidal graph. Some stars do something very regularly. Some stars are just very noisy and hard to hear. But we can break this down into its frequency components. So we can take a look at what those waves were and ask ourselves, well, what frequencies are affecting the star? And so you have an example here where Alpha Centauri has these frequencies and the sun has these frequencies. So you can see it's per hour. This is not really our hearing range, so we'll need to speed up the sound to be able to hear the sun's vibrations. And looking at this tells us a lot of information about the star itself, tells us about its rotation, age, mass, because different stars at different ages have very different interiors. Some of them have more convection, some of them are more just radiative. So there's a lot of differences in stars, and just looking at these frequencies tells us an incredible amount of detail. So how do we break those things down into their frequency components? There was this cool guy named Fourier who told us about it. He found that all sinusoidal waves can be broken down into sines and cosines. And you can, as you can see here, you've got one low frequency wave plus a slightly medium frequency and a higher frequency, and it gives us this weird thing. But what Fourier showed us is that you can actually do the opposite. You can look at this wave and tell yourself, what frequencies these are at and how loud they are. So this is extremely important. This is called a Fourier transform, and it's used all over the place. It was used to help determine when tides would show up. It's used in audio processing all the time. It's used in spectroscopy, so it's really important. And it can be done to analyze music. So here's somebody analyzing the keys of a piano keyboard. And this is somebody doing the same, looking at the phase and the frequencies. That's getting annoying, okay. But yeah, so Fourier transforms are extremely important, and probably something you do in your everyday life is using them. Remember when I said that sound needs to travel through something? I sort of lied. The truth is, there are these things called gravitational waves, and they've been all the buzz recently. Basically, when two very massive objects like black holes rotate around each other, they stretch and pull space-time around them, and they send out these stretches and deformations all across the universe. So when LIGO was able to pick up some of these sounds, what we were actually seeing was space contracting and stretching. And if you were close enough, and by close enough I mean 10 billion kilometers away, that stretching and contracting would resonate with your eardrum, probably allowing you to hear this. So this actually takes place within the frequency range of human hearing, and you can listen to it. So, yeah, you might have heard there was a very low sound and a much higher frequency sound. So the low sound is actually what you would have been able to hear if it was louder, but these are very, very small amplitude waves. So you would have been able to hear that, and the much higher pitch sound is what LIGO has changed to better to be able to, so that it's better to be heard. Basically, they've pitch corrected it. But that is the actual sound of space deforming, no medium required. So let's take a look at some of the sounds of the solar system now. Okay.
All right, thank you, Shashwat. For the next part of this presentation, now that we understand how we could actually take either radio emissions or other types of sounds and be able to translate them into something that any of us here in the audience could listen to, we're now just going to go through and actually give some examples. And in, of course, the spirit of the season, it's Halloween coming up. I'm now going to spend the next 10 to 15 minutes playing a bunch of very creepy, scary, and downright weird noises for you. We are going to start first, though, with a very important disclaimer, which is, I must emphasize that most of the sounds that you are about to hear are not what you would actually hear if you were flying by any of the planets or the sun or the moon, so on and so forth. And that just gets back to what Shashwat was talking about, that we would need some kind of medium to go through. And more importantly, these likely sources of the noises are going to be stuff like interactions due to the solar wind, interactions with the planet's magnetosphere. And so most of these sounds are going to be radio emissions that are just going to be translated into human audible range. They would not necessarily be a real sound. And if it is in fact a real sound that I'm going to play for you, I will be sure to highlight that ahead of time so that we can make sure we can differentiate between what is real and what has just been sonified for us. Because, just to emphasize, we cannot hear radio waves. It would be incredibly annoying if we could hear radio waves and you walked outside every day and just heard every radio station all the time at once. We will start, as we start everywhere with our solar system, with the sun. So what I'm first going to play for you are some natural acoustic vibrations from within the sun. And basically what we're listening to here, the sun is acting sort of like a bell. It's vibrating, those vibrations are bouncing off around the interior of the sun. We're able to record that data. And then, of course, this data does have to be sped up. This is not a real sound. This data is sped up about 42,000 times so that the frequency can be put into human audible range. But this is just sort of the general base level sound of the acoustic vibrations of the sun. This is not something that we would be able to hear if we were near the sun. If we moved the sun, say, much closer to Earth, completely disregarding all of the other reasons why that would be a very bad idea. When we're talking about just the sound that would come out of the sun, if we moved it, say, I don't know, 90% of the way here to Earth and just let it sit there, we would get something that definitely is very loud and a constant screaming. Pretty annoying. We'll now move to the planets, starting with Mercury. So this sound is going to be playing in the background while I go through this slide. Basically, Mercury has no atmosphere at all. And so there's going to be no medium for anything to travel through, and we wouldn't be able to hear anything if we were actually on the surface of Mercury. However, if there was sound, it would be predominantly due to the solar wind. It's so close to the sun, it's just getting bombarded by the solar wind constantly. And we're actually able to take measurements of the solar wind, as we have here, and translate them. So data sonification, this is not a real sound. We took measurements, or the measurements here were taken between 1998 and 2010, about 89,000 measurements or so that are sped up to make the sound that is currently playing, to give an approximation of what the solar wind would sound like. We'll now move to Venus. So Venus does have an atmosphere, quite a dense atmosphere actually, and so sound could, in theory, travel through if we were there and able to listen. And the atmosphere itself, we're actually able to record interactions within the atmosphere and translate that, data sonification, into a sound that we can listen to. So the low frequency radio signals that are going to be present would be due to interactions within the ionized gas, otherwise known as the ionosphere, or the top layer of the atmosphere. So this is a recording from the Parker Solar Probe as it flew in and out of the ionosphere of Venus. A fake sound, of course. This has been translated for us to listen to. So you're actually able to hear, as the probe enters into the atmosphere, begins to record those interactions within the top layer of the ionosphere, as it travels through, and then as it leaves, you hear the increase in the radio frequencies that it's recording. However, we can actually also hear a real, truly real sound from the surface of Venus, because we have been able to land a couple of probes. So Venera 13 and 14, this was a 1981 Soviet mission to actually land probes on Venus, do some measurements. Of course, Venus has a whole bunch of other issues. It's very hot on the surface. The atmospheric pressure is very high there. So any probes that we land are only going to survive an hour, 2 hours max, before we're just going to lose communication with them. However, on the Venera probes, I'm not entirely sure where on the probe the microphone was, but they were equipped with audio microphones. So for the time that they were on the surface of Venus, they were able to record this. Which is basically the sound of the wind that it's recording on the surface of the planet. And this is, again, a real sound. If you were able to survive on the surface of Venus, this would be something you might be able to hear. We'll now move to our own planet, Earth. Plenty of sounds we could talk about on Earth, including the sound of the presentation that's going on right now for you all. But we're instead going to focus on the magnetic field that Earth has, the magnetosphere. Basically, Earth's magnetic field creates almost like a shield around the planet at the upper layers of its atmosphere, a shield that can protect it from those highly energetic ionized particles that are just bombarding us, coming in from the sun, constantly trying to break through. The shield, what ends up happening as these particles individually come in, they sort of, or most of them, just sort of bounce off of the magnetosphere and then fly elsewhere in space. So in a sense, the shield, the magnetosphere is acting like a drum. It will vibrate like a drum when these particles hit it. That is a sound that we can record. Now these are radio emissions, so of course this is a fake sound, not something you'd actually be able to hear, but we can figure out what sort of the modes of our magnetosphere would sound like and its vibrations. So again, not a real sound, but real data from radio emissions that we're then able to translate into something that we can hear and see the vibrations of our own magnetosphere. Now, the magnetosphere itself is not perfect. There are some weak spots to it. In particular, the weakest points of the magnetosphere just happen to be at both the north and the south pole. And so at those points, it's possible that these charged particles from the solar wind can actually break through and enter down into lower parts of the atmosphere. When they do that, they'll interact with the gases that we have in our atmosphere, and they'll make some really nice pretty lights, otherwise known as the auroras. So the auroras themselves, there have been reports of people who see them that they hear some sort of crackling noise. Now, these are all unfounded. Any actual scientific experiments into the auroras have not been able to detect an actual audible sound, but you can measure the radio emissions of the auroras themselves and then once again translate them into human audible noise. And this is what it would sound like. So we do live far enough north here that occasionally it is possible for us to see the auroras if we're incredibly lucky, and of course if we get out of all the light pollution. So if any of you get a chance in the future, maybe see if you hear something like that, or hear some kind of crackling noise. I haven't been able to see them myself. We'll go to the next planet out, Mars. So there's a couple differences that we need to make sure we explain about Mars compared to Earth before we start defining sound on this planet. One in particular, we want to make sure I iterate that the speed of sound on Mars is going to be a little bit less than the speed of sound on Earth. So any sounds that would be transpiring on the planet's surface are just going to take a little bit longer. Those sound waves would take a little bit longer to get to any receiver. Also, the atmosphere on Mars is about 100 times less dense than what it is on Earth. And what that means as far as sound is that all volumes, you're just turning the volume slider down. Everything's just going to be a little bit softer. And then also, the composition of Mars's atmosphere is significantly different to our own here on Earth. The atmosphere is about 96% carbon dioxide, which means that it's going to be absorbing most of the higher frequency noises. That is a process known as attenuation. Basically, those higher frequency noises get absorbed or reflected, and the outgoing sound, what would actually travel to a receiver or to your ear, you're going to mostly hear low frequency noises. Well, we happen to have sent quite a few probes to Mars, done a lot of measurements, a lot of scientific experimentation there on the surface, and one of the more recent rovers that was sent down there, the Perseverance rover, happened to be equipped with 2 microphones, one of which is circled right here near the top, so 2 actual audio microphones that can record real sound that is taking place on the surface of the red planet, and they've recorded over 5 hours of audio signals. What I'm going to play for you now is a recording of Martian wind. So something you may or may not have seen in this video, which is trying to record the frequencies that it's hearing over the course of the audio sample, is that pretty much you're hearing all of the low frequency noises due to the attenuation that I spoke about. But that's an example of the Martian wind, and now we're going to be leaving all of the rocky planets, and this is where the sounds really start to get weird. First, we'll head to Jupiter. So Jupiter, biggest planet in our solar system, it also has a magnetic field. It is a very strong magnetic field that it has, and we have sent a few probes to do a bunch of experimentation flying around Jupiter, on the moons of Jupiter. In 2016, we're going to specifically focus on the Juno spacecraft, which is pictured here. So Juno crossed just from general space into the confines of Jupiter's magnetic field. I'm going to play the recording of what it heard. Now again, this is not going to be a real sound. These are going to be the radio emissions that it recorded, translated into human audible frequency ranges. So this is what Juno heard. Basically, when it hit that second part of the recording, the bow shock, that was when it entered into Jupiter's magnetic field, and it's almost like it hit a shock wave, just like Shashwat talked about earlier on in the slides. That's basically what Juno, the spacecraft, experienced. Again, Jupiter's got a very strong magnetic field. The fact that it has a magnetic field, the fact that that magnetic field is going to be interacting with the solar wind and particles that hit it means that Jupiter will also have auroras, just like Earth does. And those are also radio emissions that we're able to study, record, and translate into a sound. So what would the auroras of Jupiter sound like? So that's an example of data sonification for the auroras that Jupiter would experience, which would be larger and more violent than, of course, what we would get here on Earth, as is the case with Jupiter compared to most other planets. We'll now go to Saturn. We're working our way out, and we're almost at the end. Saturn, we're now going to be talking about a different probe here. No longer the Juno probe. It was the Cassini spacecraft that was tasked with studying Saturn, its moons, their interactions. Specifically, what we're going to listen to in this first audio is a recording from 2017 where the Cassini spacecraft actually measured plasma wave interactions between itself and Enceladus, one of its moons. Basically, these plasma waves interacting in a circuit, moving between planet to moon and back. These are the radio emissions, again, not a real sound, that Cassini was able to record. And for anybody who's been paying particularly close attention to this presentation, that was the sound that we played during our title slide, all the way back at the beginning. Okay, one more sound from Saturn. Cassini did a whole bunch of different experiments. It was studying pretty much every single part of Saturn that it could, and that includes Saturn's rings. We do have a recording of when Cassini traveled through Saturn's D ring. So the D ring is the closest of Saturn's rings to the planet itself. These are just a whole bunch of other icy particles and particulates that form the rings moving around Saturn. Now we're going to listen to this sound. The video is going to play over on the right. Again, this is not a real sound. This is Cassini recording the interactions that it's feeling as it's actually traveling through the D ring and all of these particles are bombarding it. And this is what sound it recorded. So you can hear the exact point where it actually really traveled through, like flew right through the D ring. However, you might also notice a couple higher pitched spurious audio signals near that latter half of the video. And the scary thing about that is we don't actually currently have an idea where those sounds are coming from or those interactions are coming from. But definitely you can hear when it passed through the ring itself. The last two planets, unfortunately, have to get lumped both into one slide, and that's because Uranus and Neptune, the two outer planets, we don't actually have data that has been sonified, at least not in a reliable sense. If it's not coming from NASA, I don't trust it. So Voyager 2 is now the probe we're talking about here. Voyager 2, maybe you heard about it if you came to our talk back in May, took electromagnetic observations of these two outer planets. That data currently has not been sonified. If we were curious as to what these two planets would sound like, well, the one thing we do know about Uranus and Neptune from our observations of it currently is that they're both very windy. If you were on the surface or within the atmosphere of Uranus and Neptune, the winds there are traveling incredibly fast, sustained gusts almost at 600 meters per second, and the sounds of either planet, therefore, would just be dominated by the sound of wind. We've made it the whole way through the solar system. There's just a couple slides on sounds outside of the solar system. Again, if you were here for our talk in May on Voyager, we actually played this sound that I'm about to play for you. Voyager 1 now, we're talking about the other Voyager probe. As it traveled into interstellar space, there was a period of time where it recorded interactions that were caused by sort of roaming clouds of plasma. We'll play that sound for you now. Couple interesting things about that to point out. One, again, not a real sound. This is Voyager measuring the vibrations that it's feeling due to those clouds of plasma, and we're able to translate that into something that we can hear. But also, if you look at the horizontal x-axis here, you'll notice, of course, that these sounds are taken over they occur over the course of weeks, not days, not minutes, not seconds, but we're talking, we have November of 2012 here and May of 2013 here. So these interactions are taking place over quite a long time scale. And the last sound to play, at least before we get into the final section, is we want to talk about the sounds of black holes. And so what I'm about to play for you now are measurements from the Chandra X-ray Observatory. This is fairly recent, within maybe the last couple of years or last year, where this observatory was actually able to measure the pressure waves that are emitted from the black hole that's at the center of the Perseus galaxy cluster. And this is just an artist's representation. It's not actually going to look like this, but it's important to take away from this image that there's a lot of material that is surrounding the black hole. That material and the gas pretty much means it's going to act as a medium. And what happens when we have pressure waves that are moving through a medium? That means that it's an actual, real sound that we would be able to hear, of course, if our ears were tuned well enough, which normally, in this case, they are not. The noises that you're about to hear are, if you were to hear them or be there right near the black hole, the sound is about 57 octaves below middle C. For any of you musicians out there, that is really, really low. That's about 200 quadrillion times lower frequency than middle C. So we just translated up 57 octaves. And this is the sound that was recorded. So if you're sufficiently creeped out by this, or any of the other sounds that I played, then that means that we did our job here today. We're going to move into the last part of this presentation. We've presented sort of the background of sound and how sounds could operate in space. So we've given a ton of examples. But for just the last part, I want to talk about why any of this could potentially be useful outside of just presenting it to you all and saying, listen to these cool sounds. Isn't this awesome? And that means that we're going to talk about something called astroseismology. Big, long word. We're going to divide it up into its component parts. What we're talking about here, we've got the root for star, astro, the root for earthquake, and study of. So essentially, it's the study of quakes in stars and why that could be useful. Of course, necessary place to start if talking about astroseismology is just to completely cut out the astro part and talk about seismology, or otherwise talk about earthquakes and the study of earthquakes. Basically, what earthquakes are, when we're dealing with them here on this planet, we've got the tectonic plates, they're sliding past each other, and it's not just a perfect frictionless slide. The friction between the two plates builds up a lot of stored elastic energy as they're moving past each other. And it can only store so much. Just like you can only pull a rubber band so far before it breaks, you can only store up enough elastic energy before it reaches a breaking point, and then all that energy is released at once, and that causes a ripple, an earthquake. It radiates those seismic waves that propagate out, and that's what we're actually able to feel, and that's what we're also able to hear, of course, if it is loud enough, because it's able to propagate these seismic or the sound waves through the atmosphere. Earthquakes, how do we actually measure them though, besides just sort of standing near a fault line and waiting for one to happen, is we can use something called a seismograph. How a seismograph works basically is you take a pen, you suspend that pen, you have the rest of the apparatus, and then when a seismic wave travels through the earth, the apparatus vibrates, but the pen stays exactly suspended. And it's shown here in the GIF down on the left. What's happening, you got this roll of paper that spins around, and the pen is able to record the vibrations of those seismic waves. And by measuring these seismic waves, by measuring their amplitude and timing when they occur, we're actually able, you can pinpoint where the epicenter of any earthquake might be occurring just by studying when the waves arrive. And if you have not just one seismograph, but 2, 3, 10, 20,000, whatever, around the world, you're able to do a lot of interesting research where you can then study the interior of the Earth and get really detailed measurements about what the Earth looks like if you just go down beneath the surface. And that can be used for a lot of interesting applications. It's obviously huge in geoscience to learn about the crust of the Earth, about the interior of the Earth. If we move outside of the sciences, it's also a very reliable way to figure out if anybody is testing nuclear bombs underground, because that obviously creates a pretty large tremor. And so you can imagine that certain people might be very interested in that. And those are just some of the implications of being able to measure seismic waves. As far as how we classify, how do we put a number to the strength of an earthquake and the seismic waves that we measure, we get to the Richter scale. That's Richter up there. Basically, this scale measures the magnitude or the amplitude of those seismic waves, but we've been able to sort of directly translate that into a way that the general public knows as the strength of an earthquake or how catastrophic it's going to be if you hear it. It makes a lot of sense to think that, a 7.0 earthquake, if you hear that, you probably think, oh, that's a big deal. And if you hear a 2 or 3.0 earthquake, you're thinking, wow, I probably never felt that. The Richter scale is a logarithmic scale, just like the decibel scale that Shashwat talked about in his part of the talk. And so that means that that 7.0 quake is going to be 10 times stronger than a 6.0 earthquake. For reference, I think the strongest earthquake that's been measured on Earth is around a magnitude 9 or 9.1, and that, obviously a very big deal. I think a magnitude 9 earthquake was the one that pretty much leveled San Francisco back in the early 1900s. So done talking about that, we need to get back into space and talk about astroseismology, not just regular seismology. So Earth isn't the only planet that can have these tremors or quakes, even if some of the other planets or moons don't necessarily have the active tectonics that Earth does. They can still experience quakes. Obviously, if an earthquake happens on Mars, it's no longer an earthquake, it's a Mars quake, or a moon quake, or a Venus quake, or a Mercury quake. And again, if you're on one of these planets, and one of these happens, and there's an atmosphere on the planet, this is potentially something that you would physically be able to hear if you were on the surface. So what I have pictured here, this is a pretty recent development actually. This is a measurement of a magnitude 5 Mars quake that one of the rovers on Mars measured just earlier this year on May 4th. When we're talking not about the rocky planets though, or the moons, and we want to instead focus on the outer planets, the gas giants, now the quakes, as we think of them, are a little bit different. They're more in line with what I was talking about when I played the sound of the sun. They're more like internal acoustic vibrations bouncing around the interior, almost like the ringing of a bell. In particular, I'll go back to the sun and focus on the study of quakes or vibrations in the sun, helioseismology. So pretty complicated subject actually, but what helioseismology is all about is using those acoustic vibrations, those oscillations, to get really detailed measurements and ideas about what the interior structure and the rotational profile of the sun looks like, things that we would not necessarily be able to do just with typical electromagnetic observations. So what this method has been used pretty widely, and we've been able to map the internal rotation profile. Basically, how are the gases inside the sun, how are they moving, rotating? We can get a pretty clear idea of that down to about 3/4 of the way to the sun's core. And that's fantastic. That's led as a secondary effect to a whole lot of other interesting physics. In particular, helioseismology was the basis for what's called the solar neutrino problem. Just a step aside here, neutrinos, fundamental particle, very, very, very light, and they're created with the fusion processes in the core of the sun. They're let out, we can record them, but there was this huge discrepancy between the number of neutrinos that we were expecting to get and the number that we were actually receiving, and nobody could figure out why that was the case. I'm not trying to tell you that helioseismology solved that problem, but what it did was provide a secondary confirmation that yes, this is a problem. It's not just our models that are messed up. This is a real issue. And then people come around and actually solve the solar neutrino problem. It was such a big deal that it was awarded not just 1, but 2 Nobel Prizes in 2002 and 2015 for discoveries that led to its solution. The last topic to talk about today. Finally, we're going to get real big picture astroseismology. Not just planets, not just moons, not just the sun, any star. Astroseismology presents for us a method, just another method that we can use to actually look at the interior, the interiors of any stars we might be able to look at in the sky. And I want to focus on neutron stars. Why? Well, if you came to one of our talks, I believe it was last April, we're very interested, scientists are very interested in what the heck is inside neutron stars, or just figuring out what the interior of a neutron star looks like. So the idea here is, could we potentially use astroseismology and those techniques to probe inside a neutron star and get a better idea of the structure of its interior? Spoiler, not yet, but we're getting there, and I'm going to provide an example with starquakes. Quakes on the level of full stars. We're going to again focus on neutron stars being this incredibly dense, I mean incredibly, incredibly dense stars of fundamental particles of neutrons that are all clumped together, spinning around. They've got very, very strong magnetic fields. And in particular, I want to focus on magnetars. Just an artist's rendition of a magnetar up here. Basically, magnetars are neutron stars whose magnetic fields are even stronger than the regular neutron stars, and so they provide excellent opportunities to study starquakes. Why is that the case? Because the current theory for what starquakes could be caused by is that these magnetic fields, and the star is spinning around, spinning around, spinning around, that the magnetic field slowly starts to kind of pull the crust too much to the point that you have so much stress that builds up that eventually the crust of the magnetar actually breaks just a little bit. And even that breaking a little bit when we're talking about neutron stars is going to be a big deal, because it's going to immediately want to fix itself and go back to a state of equilibrium. And when that happens, it releases an incredibly large amount of energy that then radiates outwards as like the vibrations of a starquake. We have an example of a starquake that has actually been measured that happened in 2004. This starquake occurred from a magnetar about 50,000 light years away from us, and again, another artist's rendition of what the starquake would look like as it radiates away, and those waves might come towards us and hit us. When that did hit the Earth, it temporarily knocked out all satellite communication because it disturbed the ionosphere, it disturbed our upper atmosphere so much. So all satellite communication was knocked off temporarily, and that scared a lot of people, in particular people like the Navy that use sonar and other satellite capabilities to figure out where the heck anything is. Of course, this was all resolved after a short period of time, but it wasn't until a little bit later that we were able to figure out, that the thing that turned off the world for a second, that was actually a starquake from a magnetar 50,000 light years away. And I'll finish by mentioning that these starquakes, of course, we have to completely shift our idea of strong. We have a 7.0 earthquake here on Earth. That's a big deal. That's going to cause quite a lot of damage. A 9.0 earthquake that happens here on Earth completely could level a city, cause immense destruction, years to fix. What would be the Richter magnitude of one of these starquakes? The answer is about 32. So I will leave you with that and ponder exactly how crazy that number is, and just mention that while this reaches the end of our talk today, I of course want to advertise our next talk in November about something that many of you have probably heard about in the news, and that is the James Webb Space Telescope and all of the amazing discoveries that it has made so far, despite only being in operation for a few months. And that's going to be the topic of our talk in November. I hope you all join us, and thank you for coming today. And we're also happy to take any questions at this time. Yes?
Today's talk was really interesting for anyone who is into music and sound or astrophysics, and you two are obviously very into astrophysics because you're musicians, but I was wondering if the two of you have any connection to music or sound as well.
Okay, so the question, in case it didn't get picked up by the rest of the audience or by our live stream, was the talk today obviously had a lot of connections between music, sound, and astrophysics. I think it's hopefully obvious to the audience that both Shashwat and I are interested in astrophysics. But the question is, do we have any secondary interest in sound, music, or otherwise?
Yeah, I can go first. I do know how to play the guitar, kind of. I like to think I can sing, but I think Gabe's answer will probably be more interesting.
My answer is I can't sing, but I can play piano. So, yeah.
Any other questions? Yep.
What about sound from the Earth going out? How far does the atmosphere stop? It sounded to me that somebody was on a planet besides Earth. Could they detect an atom bomb?
Right, so that's actually a really good question. The question was, what about sounds from Earth going out into space? So you mentioned how many of them can escape the atmosphere and atom bombs, right? So about the atom bombs, that's actually interesting because people have been able to detect atomic tests from other places. Kodak was able to find atomic tests because their film was affected by the radiation. So it does bounce around a little bit, but sound can't really escape the atmosphere. There is a diagram that they have of our radio waves. So humanity has been using radio signals for about 100 or so years now with radio technology. So we do have a sphere of those radio waves that we've sent out, and they've gotten about 100 light years from here, but that isn't far enough. So anything out there that may have heard us would take about another 100 light years for them to send us a message back, which isn't cosmically long, but fortunately we won't be there for that.
But yeah, that basically, if we consider the second part of this talk, we're listening to different sounds, and some of them are real that we can actually hear, and some of them are just sonified from radio waves. It's that second bit, the ones that are sonified from the radio waves. That's what could actually escape our atmosphere, can send out a radio signal, and anything else out there, if they tuned their dial enough, just like we do in our cars, we might be able to, or they might be able to hear that. But actual sound, us talking here, would not get out of the atmosphere.
Yeah. But, oh, sorry.
Or after you.
Oh, I was just going to
Oh,
say, the shock waves sometimes can circle the Earth. So when, like, the volcano went off, the people were able to hear the shock wave travel across the Earth, like about 3 times or so. So it's it does move around. I'm sorry about that. Yeah.
So like, you give me like a scale to measure a 32 earthquake, like could it destroy an Earth-like planet or maybe a star or something?
A magnitude 32 earthquake would almost certainly absolutely eradicate the Earth. I mean, a 9.0 earthquake is already going to destroy entire cities. A 10.0 earthquake is 10 times stronger than that, 10 times stronger than that. You keep going up all the way to 32. A magnitude 32 earthquake is something that we have no scale for what kind of damage that would cause here on Earth. Catastrophic doesn't even begin to describe it. As far as for stars, in particular the example that I had at the end of the presentation. So this magnitude 32 starquake is not destroying the star. It's the result of the crust of the neutron star just getting ripped ever so slightly, and it's the force of that coming back together, going back to equilibrium, that it releases seismic waves that are the equivalent of what we would think of as a magnitude 32 earthquake. So it doesn't destroy the star, it almost kind of fixes it, but it would destroy pretty much everything else.
Yep, that's a question I was asking. It's like, hi, Red Dwarf. Hi, young dwarf. Hi, you giant. Want to get annihilated?
Are there any sounds on the moon?
Not within the atmosphere. The atmosphere is pretty much non-existent on the moon. I guess moonquakes would be a thing that you might be able to feel the vibrations of. Yeah, it's
Yeah.
there are old lava tubes they found on the moon, but I don't think it's tectonically active at the moment.
No, yeah, there would be moonquakes, but without with a lack of an atmosphere, it's not going to be a real audible sound that you'd be able to hear.
Like the last one of the lunar landings, they sent the lunar lander back into the moon, and they were able to pick up a quake, given our Earth shape. They said the moon ran like a bat.
Really? Okay. I didn't hear that.
Yeah, they've seen the
Yeah, when they landed. Okay. Oh. That's cool.
Mhm.
Any other questions?
And if you think of something, feel free to approach us afterwards. We'll be here for a little bit longer as we take everything apart. But thanks again for coming today. Hope to see you next month.
Yeah, thank you so much. Thanks to Anodyne.